Hello, everyone. This is our second lecture. It's on causation. We're going to talk about logic models, what are called DAGs, and potential outcomes. There are different ways of thinking about causation. It's a really important topic for basically all of us, and so I think going through this very stepwise is going to be very helpful as we're thinking about what causation really means. So causation. Generally, in our fields, the majority of the research is dealing with causal relationships. You have some that are just looking at understanding prediction, where can you predict this thing that may happen, or predict uh, a disease or a disorder. But that's not as common as trying to understand causal relationships. When I say causal relationships, we're really talking about things like, does this intervention work? Does this behavior cause later problems or later benefits in life? So when we're talking about causation, then, what do we mean? Well, simply, X causes Y if, when X changes but nothing else changes, Y changes. So I'll say that again. X causes Y if, when X changes but nothing else changes, Y changes. Another way of thinking about this is X causes or influences Y. It's unlikely that X is going to be the only cause of Y. So whatever your outcome is, it's not going to be the only cause, whatever your predictor is. Consider a few examples. You got rain causes my lawn to get wet, but so do my sprinklers, my kids playing with the hose, etc. So because rain causes, in the term of causation, my lawn to get wet, doesn't mean it's the only way that my lawn will get wet, but it still is a cause. So I want you to consider these three examples, which are causal. Earning a graduate degree increases income. Lightning causes thunder. Tanning causes skin cancer. Are all of those causal, or only some of them? So on their face, the face value of this, yes, it makes sense. If you get a graduate degree, your income is probably going to go up. However, anytime we're talking about a causal relationship, there's also an element of probability. So with earning a graduate degree, your income may not go up. It's more likely to go up, but it may not. When it comes to tanning causes skin cancer, there's probably a number of people that go tanning quite a bit and do not get skin cancer. Why would that be? Well, there's a number of reasons, right? So there's genetic factors. There's other reasons that their skin may be uh, more able to handle the tanning, the radiation. But still, we can say tanning causes skin cancer. And the way that we're normally going to say that is that tanning increases your risk of getting skin cancer. It doesn't mean that you will get skin cancer, it just means that you are more likely to. When it comes to lightning causes thunder, I think this one's really interesting. Face value, it's yes. You see a lightning strike, a couple seconds later, depending how far away it is, you hear thunder. So what does that mean? It means, depending on how we're looking at the relationship, we can simply say, yes, lightning causes thunder. But if we want to go at an even deeper level, we could say lightning causes a rapid heating of the air. That rapid heating of the air then causes a shock wave. That shock wave is then transmitted long distances, and then it hits our eardrum, which is then interpreted in our brain as noise that we can interpret as thunder. So even though, yes, lightning causes thunder, depending on what level we are analyzing lightning and thunder, it's going to depend on how we even talk about that relationship. My point of bringing these up is that causal relationships are complex. They're not easy to just say this causes this. But sometimes we're able to say it's going to increase your probability of having a bigger income or increases your risk. Or we could say, yes, it causes it, or it causes something that then causes something that then causes the thing like thunder. For a more formal definition, we really need to show three main things if we want to show causality. So regardless of all the levels that we want to show causality, the three things that we need to have, the first one is there has to be somewhat of a correlation. You need, when one thing happens in one variable, something needs to happen in another. It can be this one goes up and this one goes down, or this one goes up and this one goes up. That doesn't matter. And the correlation can be defined in a lot of ways, but when one moves, the other one also needs to move. The second one is X happens before Y. This makes sense. In order to cause something, the cause needs to happen before the effect. And then third, all other factors need to be ruled out. We'll get into with all other factors being ruled out, we need to say all these other things that could be the cause of this relationship between these two things. We need to be able to show in one way or another that those couldn't be the reason why those two are related. That is often the most challenging part of showing causation. It's not too hard to show a correlation. In this class, we're going to show lots of ways of showing relationships. In other classes, you've already shown that in other stats courses. X happening before Y, that one makes a lot of sense. You can show that this happened and then this happened after. But the difficult one is that all other factors need to be ruled out. What we're going to focus on basically for the rest of this is understanding how do we work with that? How do we understand how we can actually rule out all other factors? The first approach we're going to talk about is called logic models. It's a basic representation of what you believe is the cause-effect relationships. And it's usually drawn out as a diagram. You see these a lot in program evaluation where you're trying to understand how is this program or intervention producing the results that the program wants. This is a very simple example of it. Generally, you start with inputs. It's all the things that are needed to create the outputs, like funding, the research design, all of that stuff. That's going to produce the outputs, which is what we're actually going to do and who we're going to do it for. The outputs are really the action part of the logic model. We're going to take the inputs to do something to really affect someone or something, which then will produce outcomes, what we actually want to happen by doing the outputs. Along with those ideas, inputs leading to outputs, which lead to outcomes, in a logic model, we need to highlight the assumptions that we're basing these on and other external factors that may be influencing how the inputs, outputs, or outcomes actually happen in real life. We won't really use logic models much in this class. It's really common, like I said, in program evaluation, and there's this YouTube video you can watch on your own time if you're interested in learning more about it. They're very good ways to show what you believe is happening in a program or what will happen in a program if it's implemented. For this class, we're really going to focus on directed acyclic graphs, or DAGs. And DAGs are super useful to decide how we can rule out alternative explanations. It's one way that you can get more experience with this is looking at this book. It's called The Book of Why. It's a great one. It's about the science of cause and effect, and it uses these ideas, these DAGs. So here's an example. This is a DAG right here, a directed acyclic graph. We have education, which leads to income. The education is, in this case, it has the arrow going from it to the income, which means that it is the cause and income is the outcome. But if we really think about this, what else causes changes in income? Is it just education? Well, we probably could add a number of things. For example, we could say the location. Where do you live? If you live in a rural area, your income is going to be different, but also your accessibility to education, your access to it, will be different. So you see location is pointing to both income and education. It causes both. So depending on where you live, it'll influence how likely you are to get more education, and it's going to influence your income. Another one, let's say work experience. So work experience may not cause education, so we don't have a relationship there, but it may cause income. As you get more work experience, you're usually worth more, and so your income goes up. So that's another way that this other variable, other than the ones we're interested in, education and income, might be affecting the system. So we have work experience impacting income, we have location impacting both education and income. We have graduation year, and this is especially relevant considering the recessions we've had and the pandemic, where if you graduate during a pandemic or during a recession, that's going to impact if you go get more education or if you go get a job and how highly paid that job is going to be. So that's an interesting one that you might not think of right away. Maybe you did if you graduated in a bad year, but graduation year causes both education attainment and income. So that one is similar to location, where it is having an influence on both of our variables that we're interested in. And of course, there could be others. I don't list all of them here because there's quite a few that can influence income and education, including socioeconomic status to begin with, your race, gender, stuff like that. Another example of a DAG would be, let's say we're interested in a mindfulness practice and how that influences well-being. So we can think about what other things would influence a mindfulness practice, someone choosing to participate in a mindfulness practice, and their well-being. So there's going to be some variables that impact both. For example, socioeconomic status could influence if someone decided to practice mindfulness because maybe they have access to a yoga studio or instructors, and it's also going to influence their well-being. There's also going to be some things that just influence well-being. It has nothing to do with mindfulness practice, but it has something to do with well-being. What a DAG allows us to do is think through this in a very rigorous way where we can say, these are the things that we can see in the literature, that we can see in practice as clinicians, if you're a clinician, that are impacting these variables. It's a very transparent way to say, this is These are the things that we think are influencing this relationship. If we want to define it better, we need to look at what one of another book, it's called Statistical Rethinking. I think it is fantastic. In there, he puts the 4 elemental confounds, and I think they're really useful: the fork, the pipe, the collider, and the descendant. What's important about these is that the fork, that's saying we're interested in X and Y, how they relate to each other, and we have this other variable. And this fork, this is saying that this other variable is actually causing both X and Y. Maybe X and Y still have a relationship outside of that, but Z is causing both of those. If we go back to our DAGs just a second ago, one of the Z's would be like location or graduation year. They're causing both education and income. So what does that mean? Well, it says it's open unless you condition on Z. In other words, we need to control for Z in some way in order for us to really understand the relationship between X and Y. If we don't control for Z, then the relationship between X and Y has this additional power because Z is there too. And it's going to make X look like it's really predictive of Y, that it really explains it, it causes it a lot, even if it doesn't, or maybe even if it causes it a little. So the fork is where Z causes both, and we want to control for Z. Similarly, we have the pipe, and this is where X causes Z, which then causes Y. This is often considered a mediation pathway where Z is the mediator. You have X causing Z, which then causes Y. It's this pathway effect. And again, if you're interested in understanding the relationship between X and Y, not between X and Z and Y, then you need to control for Z. The descendant is very similar to the pipe. All it's saying is that conditioning on A, in other words, if we don't have Z measured, but we have A measured, then if we control for A, it's similar to controlling for Z. It's not perfect, but it's going to be similar. And the more that A and Z are related, the better controlling for A is in place of Z. In other words, if we know that we should control for Z because we're interested in the relationship between X and Y, but we don't have it measured, if we have something that is also caused by Z, in this case A, then we can control for A, and that will be like controlling for Z. Now the collider, I save this one for last because it's the most unique. This is where both X and Y are causing Z. When X and Y cause Z, it makes it look like X and Y are related when we control for Z, even if they're not related. So this is the one case, the collider, where you do not want to control for Z, because it'll make it look like artificially that X and Y are related. But it's just because both of them actually cause Z, and if we control for it, it brings them together and makes it look like they have a relationship. So each of these are versions of a DAG. You can see them as elements that you can use. So if you have a full DAG of trying to understand what the relationship between education is on income, you may have a number of forks in there. You will have a fork that's location, another fork that's graduation year. You might have a pipe. You might have a descendant situation. And you might have a collider. These are all different parts of a full DAG of what you're trying to explain. What this helps you with is it helps you understand what things do I need to control for and what things should I not control for. And if you're transparent about what your choices were, it makes it much more simple to debate what is real and what's not because we have a framework to work from. We have a framework to say, well, we controlled for z because we think it's causing both x and y. And in order to get that effect out of there, we needed to control for it. That's a very helpful way to be able to discuss results and findings and help science move forward. Similarly, I think DAGs and potential outcomes are similar in a lot of ways. They are different in important ways. What potential outcomes is looking at is not this network of relationships, but instead is just asking the question, the outcome from a change in the predictor versus what the outcome would have been without the change. It's a very simple idea, but very difficult to show. So it's basically saying, if we made the change and now we know what the outcome is, the question is, what would the outcome have been in some fictitious world if that change hadn't have happened? This is often what people think of with causation, like, oh, because that happened, it made the outcome change from what it would have been. I like the framework in that it's intuitive, but it is, again, difficult to show this. So here's an example. Let's say we're looking at the relationship with health and some exercise over time. So we have time as the x variable, we have health as a y, and we're seeing that the health after starting to exercise, it improves, it goes up. And then we also see that what health would be without exercise. It's pretty flat, just kind of stays flat. But what's the issue here? The problem is we can't have both. We can't have the same person with the same characteristics and the same everything have both happen to them. Only one gets to happen. The other one will never happen. So how do we work with this? Well, in ANOVA, the ANOVA class, and in regression, there's going to be some ways that we can try to make inference about what it would have been like in one way or another. We're going to use control groups. We're going to use situations where we can match people based on certain characteristics. Those are things that can help us understand this. But again, we can't ever fully get there because we'll never be able to have both situations play out. We only can have one. So just to clarify, because we can't force physics to work with us where we can have both things happen to the same person, what we're going to try to do is make reasonable comparisons. So we have some group that they start exercising. We have another group that doesn't. And if those two groups are relatively similar in their characteristics and health and everything at the start, then maybe we can start to understand what exercise is doing. But again, in the framework of using DAGs, we can see that there might be other influences that are happening to one group or the other, or both, that could influence this. So I gotta say, throughout the class, we're gonna be talking about some elements of causation. We'll bring up DAGs and potential outcomes here and there. The idea is that regression, the promises that it has, are going to be things that we're going to try to use in order to find causation. That includes using control variables, and we're going to talk about what that means and how we can use them in very particular ways to make them most useful. But there's always a possibility that we're going to come across the situation where we are wrong. There's this really awesome website. It's called Spurious Correlations. And Tyler finds a bunch of correlations that look really solid statistically, but don't really make any sense when you actually think about the causal relationship. This is an example of one. So the number of people who drowned by falling into a pool correlates with films Nicolas Cage appeared in. I think this one's super funny because people can reason about it and be like, well, films that Nicolas Cage are in are horrible, so people are just jumping out of their windows into pools and dying or something. The fact is there's really no real relationship. But if you look at the data over time, you see that they kind of follow each other pretty well. And one problem with being human is there is a way for us to always find a way to make it justified. Like, oh yeah, those are related. That makes sense. There's always a way to make sense of some relationship and start to think it's causation. But in this class, we're really going to be rigorous about that. We're going to say, can we say this is causation? Are there reasons why we can't? And in this case, we probably could come up with a bunch that could help us understand why are these two related. That has to do with a third variable or a fourth, a fifth, a bunch of other variables in a DAG that would be like, oh yeah, these aren't actually related when you control for all of these other variables. So the idea is just to be careful, have fun with it, but be careful. When we're talking about causation, we want to talk about it in really structured ways so that we can really have a debate about what needs to be improved or what is really solid about a study. So I love this. Hopefully this is a good way to end this lecture. In those open office spaces, I love this idea. Just tape a note to your back. Don't talk to me. I have no self-control and will talk to you for 3 hours and achieve nothing. And then in small font at the very bottom, it says, thanks, I love you. It's just a good way to live life. So the next few lectures will actually get us into regression. And we're going to start to introduce how regression fits into this causal framework and how we can use it to our advantage. But keep all this in mind throughout the whole class. It'll keep coming up. Reach out if you have questions about it. The ideas in here are complicated. If you get really far into it, you can really start to sense how complex causation really can be in practice. But you have to remember, science is all about doing everything that we can to produce useful information. And having this behind you actually makes you a stronger individual, a stronger researcher to be able to show ways that it is causal and ways that it might not be.